All right, lipid metabolism. We do have lipids stored in the body, and these lipids are typically stored in what? What are our fat cells called? Adipocytes. And collectively, all the adipocytes then would be adipose tissue. Now, the process of producing lipids is called lipogenesis. Glucose 6-phosphate can enter into the lipogenesis cycle. Now, triglycerides are used as an energy source. In fact, gram for gram, they produce quite a bit more energy than glucose would. Now, if we compare a 6-carbon glucose to a 16-carbon fatty acid, or 16-carbon triglyceride, we're going to get about 129 ATP molecules compared to 36 to 38 ATP with glucose. So we can get significantly higher theoretical yields of ATP. But before we can do that, there has to be a process to prep these lipids for use. And here's what it looks like. So our stored triglycerides are broken down. Remember, triglyceride consists of a glycerol molecule and 3 fatty acids. If you're not sure about this, you may want to go back and review Chapter 2, which is chemistry, and the organic molecules. So the stored triglycerides are broken down into the glycerol and to the 3 fatty acids. The glycerol can actually enter and be converted into pGal. Remember pGal from glycolysis? That's what's oxidized, while at the same time the NAD is reduced. So that can actually yield some ATP for us. But then the fatty acids can yield ATP as well. What we see happening is that the fatty acids have to go through a preparation process called beta oxidation, and I will walk you through that today. And then the product of beta oxidation is actually acetyl-CoA. And that acetyl-CoA enters into the citric acid cycle, just like we saw that the oxidation of pyruvic acid produced acetic acid. That became acetyl-CoA and entered into the citric acid cycle. This is the same acetyl-CoA. It's just produced from a different substrate. So let's take a look at this beta oxidation process. We'll just look simply at a 6-carbon fatty acid. 6-carbon fatty acid is going to have a carboxyl group on the end, which is a double bond oxygen and a hydroxide. And then, of course, there's going to be hydrogens attached to all these. So the term beta oxidation comes from the fact that the second carbon here is the beta carbon. The first carbon is the alpha carbon. What beta oxidation will do is it will break the bond between the beta carbon and the gamma carbon, which is the third one. It breaks the bond between those 2 carbons. And what results, when all is said and done, is ultimately an acetyl-CoA molecule, which has 2 carbons to it. Now we still have 4 carbons left on this fatty acid chain. So beta oxidation will occur again. This now has become the alpha carbon, and this the beta carbon. So now we break the bond between the beta carbon and the gamma carbon. And this too then becomes acetyl-CoA. And these last two carbons then also become acetyl-CoA. And those acetyl-CoAs will enter into the citric acid cycle. They will react with oxaloacetic acid, that 4-carbon molecule, to produce citric acid. And then it goes through the process like we walked through.
Is that just a hydrogen on the first carbon?
Say that again?
Is that just a hydrogen on the first carbon?
That's a hydroxide.
Oh, good job.
I won't have you draw these, but I wanted you to see. So from a 6-carbon fatty acid, we're going to get 3 acetyl-CoA. From a 12-carbon fatty acid, we're going to get 6 acetyl-CoA. What's the mathematical formula we can use to determine how much acetyl-CoA we get from a fatty acid chain? Divide by 2. So if I said a 38-carbon fatty acid chain, how much acetyl-CoA would we get? 38 divided by 2 is 19. And we get 19 acetyl-CoA molecules. Oops. Here's the other thing. Is that for every acetyl-CoA that we produce, in the process of producing that acetyl-CoA, we're going to get 1 FADH2 and 1 NADH. Now this acetyl-CoA molecule, as I said, enters into the citric acid cycle. And that would look like this. So here's acetyl-CoA right here. It would basically enter at this same point, react with oxaloacetate to produce the citric acid. And then it would go around here. So not only do we get these electron carriers, NADH and FADH2, just from the beta oxidation process, we also get these electron carriers from the citric acid cycle as well. So we get an NADH here, we get an NADH here, NADH here, FADH2 here, and what do we get here? We get an ATP. So theoretically, for every beta oxidation event where we're producing a 2-carbon acetyl-CoA, we're going to get 1 FADH2, 1 NADH, And then from the citric acid cycle, we're going to get 3 NADH, 1 FADH2, 1 ATP. Say that again?
Can you go back to the slide that you just had, that last one?
This one?
No, the one that you drew out of the...
What do you need to see? I'll have to draw it again.
Oh, that's fine, don't
No,
worry.
I can do it.
It was just the matrix reaction that was the citric. It was the citric.
Oh, right here? Right there? You want me to draw that again? Where the acetyl-CoA came in here?
No, not that one, before that. The last slide that you wrote, you set a blank slide and you drew the 6 carbon thing and then you did like 1 every...
Gotcha, sure. So this, if we follow that all the way through, we're going to get 1 FADH2 in converting that, and 1 NADH from converting that into acetyl-CoA. The acetyl-CoA then enters the citric acid cycle, and we would get 3 NADH, 1 FADH2, and 1 ATP. But now repeat that 2 more times. And I'll just abbreviate these for short.
I just didn't know if the last 2 were the same as the first one.
This last 2 here?
Yeah.
Yes, they are. Yes. What happens is that when this is cut off, this carbon then, which was this before, this gamma carbon becomes the alpha carbon and takes on this. So yes, it does. It's the same thing.
You have to just break off the 1 and 4 remain, or is it?
It's 2 at a time.
Right. Well, I meant you break off the first section. Will the other 4 just sit there, or is it pretty conclusive that you're going to break it off?
I would say it's a pretty. I mean, it's a fast process enzymatically. Where the next one, once it's formed into that carboxyl group again, then you get that process occurring a second time. So if we look at our yields here, from this 6-carbon fatty acid, how much FADH2 do we get just from the beta oxidation part? 3. How much NADH? 3. How much NADH do we get from the citric acid cycle part? 12. Or excuse me, 9. And then we get another 3 FADH2s from the citric acid cycle, and then we get 3 ATP. And we know, well, if we add our totals up again, so we have a total of 6 FADH2s, 12 NADs, 3 ATP. Because we got 3 FADH2s here and 3 here. So 3 from beta oxidation, 3 from the citric acid cycle. Remember, each acetyl-CoA enters the citric acid cycle, or has the potential to.
So the top, the first FADH and NADH is from the beta oxidation.
Mm-hmm.
And then the bottom might have the...
Correct. These are from beta oxidation. These are from the citric acid cycle. Because remember, that acetyl-CoA right here has the potential to enter into the citric acid cycle. It may not always, but the potential is there. This is the theoretical yield. Now we know that each FADH2 can yield up to 2 ATP, right? So how much ATP would we get from those 6 theoretically? 12. And how much theoretical yield per NADH? 3 ATP per NADH. 36 plus our 3 ATP. And how much does that give us? 51 ATP. Now that's just from a 6 carbon. Just from a 6 carbon fatty acid.
So that's not a triglyceride.
That's just the fatty acid of the triglyceride. What if we had this? What if we had a 22 carbon fatty acid? Not triglyceride, but a 22 carbon triglyceride. How much ATP would we get from that? So think about what happens with one cycle of beta oxidation. How much FAD do we get from the beta oxidation? How much NADH do we get from the beta oxidation? And then how much NAD, FAD, and ATP do we get from the acetyl-CoA as it goes into the citric acid cycle? Calculate that and then multiply it by what? 22 carbons divided by 2 times 11. Go ahead and try and figure that out. How much FAD do we get just from the beta oxidation? Beta oxidation just refers to 2 carbons at a time. So the first 2 carbons. You should already know how much product we get from the citric acid cycle. You should already know we get 3 NADH per acetyl-CoA, 1 FADH2, 1 ATP. We're just adding now something a little extra. FADH2 and NADH from the beta oxidation process. So if we add all these numbers up, 1, 2 FADH2s, 4 NADHs, 1 ATP times 11 times 11, so that's 22 FADH2s, 44 NADHs, and 11 ATPs times 2, because 2 FADH yields, or 1 FADH2 yields 2 ATP, so that's 44, times 3, because every NADH has the theoretical yield of 3 ATP, that's 132, and then our 11 ATP that we already have gives us a total of what? 187 ATP from that 22 carbon fatty acid. It's a lot of ATP. Now that's obviously a theoretical yield. Won't always get that. In fact, using lipids exclusively as an energy source is not really a good thing. Problem is that because so much ATP is able to be produced, that the cell doesn't need all of that ATP. And what we get is an excess of acetyl-CoA. Not all the acetyl-CoA will actually go through the citric acid cycle. If there's too much ATP, citric acid cycle will stop, and that acetyl-CoA has to take another pathway. It's actually converted into ketones, or ketone bodies. 3 in particular. Beta hydroxy butyric acid, acetoacetic acid, and plain old acetic acid, or acetone, sorry. So we found a way to get rid of the acetyl-CoA, but the problem is these ketones. Some tissues can use these as energy sources. Others cannot. The brain, particularly, does not like to use ketones. It can under starvation conditions, but it would prefer not to. Now, if these ketones are formed faster than they're processed, that can be a real issue. It can lead to an accumulation called ketosis or ketoacidosis, where the blood pH gets seriously low. The blood gets much more acidic than it should be. These ketones will impart a fruity odor to the breath and to the urine. One of the ways they're eliminated is through processing in the kidneys and through expiration, breathing them out. Now, 2 of the conditions that typically result in the production of these ketones and the reliance on lipids as an energy source are fasting, like severe fasting or starvation diets, like the Atkins diet, and diabetes mellitus. In diabetes, people with that have problems getting that glucose into their cells. So, one of the ways that they generate ATP then is via beta oxidation, breaking down those fatty acids to generate ATP. And we know that that produces a lot of ATP, more than the cell needs. You don't store ATP. And so what happens is that acetyl-CoA then is converted to those ketones. Ultimately, in really, really severe cases, this ketosis can lead to death. Now, on that Atkins diet, that starvation diet, where you're starving your body of carbohydrates in order to burn lipids and burn fats as an energy source to lose weight. Problem with that is, as I said in the previous slide, the brain doesn't like to use ketones. And the fact that the brain prefers using glucose as its energy substrate. So we got kind of a double whammy there. We have very few carbohydrates that can be used for generating ATP. And we have the production of ketones because of the high amounts of lipids. So the brain has to adapt, but it doesn't always adapt the same for everybody. Some people have no problems with that Atkins diet. Other people can get very nauseated, headaches, get very disoriented, and they can't do it because they need those carbohydrates. Other people can adapt just fine.